In today's session, we're going to be looking at intracranial hemorrhage. Here we have a CT scan of a brain shown over on the left side in a multiplanar reformat. We have the axial images, the sagittal images and the coronal images shown. On the right of the screen, we have the axial images zoomed up. Let's have a look at this CT head. I'm sure you've all noticed that there's a major abnormality on the left. As we can see here, we've got a crescentic shaped density overlying the left cerebral convexity, in keeping with a subdural hematoma. So hemorrhage can have varying appearances on CT, but predominantly in the acute phase will appear as a bright structure. On the coronal images, we can see that there's a gradient with more bright or hyper attenuating areas posteriorly and more hypo attenuating areas anteriorly, and giving this gradient appearance. This is what we would expect to see if there is a mix of acute and chronic blood products. When we describe it, we should talk about the density, as I've already explained, the shape, the size, the position, and the effect. When we talk about the size, we can see here this is at least a moderate-sized hematoma. We can tell that because of its effect. It has squashed the underlying brain parenchyma. That is also well appreciated on the coronal reformats. If we compare the sulci, such as here, and also on the opposite side, we can see that many of the sulci underlying the hematoma have been obliterated or effaced. And therefore it shows that there's a lot of pressure being generated by this hematoma. It is extending from the frontal regions all the way posteriorly to the parietal regions and almost occipital. Furthermore, we can see that it has squashed the left lateral ventricle, shown here. This squashing has also meant that it's resulted in compartmental herniation. What that means is that the left frontal lobe has been pushed to the right and it's slipped under the falx cerebri, shown here. This can cause ischemia or even infarct, if persistent. When we get this much of midline shift, we should also be thinking about hydrocephalus, or increased pressure within the ventricular system. We look at that by looking at the temporal horns of the opposite lateral ventricle, depicted here, also seen nicely on the coronal images. This increases in size when there is hydrocephalus, as is in this case. Next, we need to look at whether the pressure has caused any tonsillar descent. Here we can see the cerebellar tonsils, and we can see that the ones on the left are quite low. The one on the right is in a more normal position. So it's starting to crowd the foramen magnum. We can see that on the axial images if we keep scrolling down. As you can see here, this is the foramen magnum. There is still CSF space depicted by the dark density around the spinal cord and the brainstem, but this is on its way to tonsillar herniation and coning. These are the most important things to look on this scan, given the significant abnormality and the effect that it may have in the acute setting. It would be important to notify the neurosurgeons at the time of looking at this scan so that management can be sought in the form of evacuation of this hematoma. From a radiology point of view, it would also be important to look for other areas of hemorrhage and also to assess the bones, for example on these settings here, to look for any fractures, and also important to look at the soft tissues to assess for any scalp or subgaleal hematoma.
Find us on Facebook, Instagram, and subscribe to our YouTube channel to help explain the mysteries of the brain.